Now let me introduce with the second divide and conquer sorting algorithm, which is quick sort, right? So the quick sort is more practically important sorting algorithm, while merge sort guarantees or n log n performance. Quick sort often outperforms it in practice due to better cache efficiency, right? The core idea behind the quick sort is different from the merge sort. So in merge sort we have divided the array into halves until we get the elements, right? So here, instead of dividing the array into equal halves and doing the hard work during merging, what quick sort does is the hard work was during the division, right? The algorithm picks a pivot element and rearranges the array, right? So that the all elements less than the pivot come before it, and all the elements greater comes after it, right? This is recursively sorts the subarrays on each side. Okay, think of it in this way. If you are organizing books on a shelf, split the books into 2 piles, right? Sort each file separately and then carefully interleave them, right? Quick sort would pick a book as a reference point, which is we call pivot here, and put all the shorter books to its left and all the taller books in its right, and then repeat its process on each side, right? So the partition is the heart of quick sort. It determines how the array is divided and how efficient the algorithms will be, right? A poorly chosen pivot leads to unbalanced partitions and poor performance. Okay, a well-chosen pivot leads to balanced partitions and excellent performance. Okay, so let's discuss this with an example. Right? Imagine this is the array, right? This is the original array, which we have 52, 27, 37, 63, 14, 17, 8, 6 and 25. Okay, so what we will do, if the pivot we have selected as 25, you take 25 to the mid, and then you have to do what you have to do. You have to take all the elements which is less than 25 to the left half and which is greater than 25 to the right half. Okay, so compare 25 and 52, right? So it is not less, right? It is greater, so we input here. And 37, which is also greater than 25, we put here. And again you have 63, which is greater than 25, we input here, right? Then 14, which is less than 25, so we insert that into left of this pivot here, right? And again 17, 8, 6, all are less than 25. Okay, so we input all this here, right? then what we will do? Again we get a pivot, right? So this is not sorted, right? And this is also not sorted. Again we have to take a pivot. I will choose 6 as the pivot, okay? And then compare these, okay? 14 is greater, right? If we take the 6 element just like this, right? 14 is greater, right? So we inserted the right? And also 17 is also greater, so insert it to the right. 8 also greater, so we insert 8 also here, right? So again this is also not sorted. What we will do? Again you have to choose a pivot. I will choose the 8 as the pivot, and again we compare, right? So what we will do? Now you have 6 and 8, right? So greater elements than it, here you have 14 and 17, right? You keep them in right? So again you have to choose a pivot until you atomize those elements, right? So you choose 17 as the pivot again and compare again. 14 is less than 17, so we insert it to the left, and the sorted left is 6, 8, 14 and 17, right? Now we have this right subarray, which is 52, 37 and 63, okay? So we initially took the 25. Now we get the right subarray, which is greater than 25. Now we need to choose a pivot for this in order to solve this, right? So we have 63 as the pivot element. Now we will compare this, okay? So 63, 52, right? 52 is less, so we insert it to the left, right? And again we have 37, which is also less, right? So we keep this as it is, okay? And then again we have to atomize this. What we will do? You choose a pivot, right? So I will choose the 37 as the pivot, and again we compare, right? So 52 is greater than 37, so what we will do? You insert it to the right? So we atomize the array, and then what we will do? You just need to combine these. You have the left subtree and the right subtree, sorted parts, and the pivot in the middle, right? So we combine, and this is the sorted array. And remember that this is not the actual way to solve the quicksort problem. This is just for simulation I am using, and I will discuss quicksort problems in problem discussion session, okay? So this is just for getting an idea, right? Now let's discuss about the quicksort algorithm, right? It's like this. Here you have quicksort array first and last. We have given the first and last element. If the first element is less than the last, right, we split the partition, we partition the array right? So we sort the left side as well as the right side, right? So initial code is like this: array 0 to n minus 1. So when the subarray has 0 1 element, it means it's already sorted, right? So let's compare quicksort complexity, right? So you have pivot always split the array into half, and levels we have to go to different sub levels which has log n, log 2n time complexity, right? And for each level we have to compare those elements. So we get on time complexity. So we totally take n times log n, which is O log n, right? So think of like the worst case, if you choose a pivot as the smallest or the largest element, right? So we have array already sorted on reverse sorted order, and one subarray has n minus 1 elements and other has 0. So if the pivot is small, right? So we have not get any things to left or the right if the array, the pivot is small or either large, right? And we have n levels, and work for each level is on. So the complexity becomes on square, right? And average case we get n log n, and the space complexity is log n for recursion stack, right? So just test with already sorted array as well as, and also take the pivot as the smallest element and partition them, and also check with the largest element as a pivot and partition the array, and check whether these are understood. Okay, so these are the comparison summary of merge sort and quick sort, right? The complexities, right? So the pivot selection strategies, as I discussed earlier, the worst case occurs when bad pivot is selected, and you have to choose random element as a pivot. So it makes worst case highly unlikely, and randomize the quick sort is practically the fastest sort. And if we choose the middle element, like if we take the median, take the first, middle and last elements, and you have to choose the median as a pivot, and it also reduces the chance of the worst case, right? And also we discussed first and last element. So if the whole array is already sorted, it is bad for time complexity, and this is easy to understand. So you can test this code. This is in Python, and you can test it in any language, and just try to insert and partition those elements and get the output, right? And also you can take the output from different partitions, right? So this is a quick summary, and you can partition using pivot. Okay, so when to use which? So you have to choose merge sort when the stability is required, right? It means, but when should you use merge sort, when should you use quick sort, right? So you need to choose merge sort when the stability is important, meaning equal elements must keep their original order. It's also better choice when you need guaranteed time complexity performance in the worst case like O n log n, right? When working with linked list, which we'll be discussing in later of this session, where merging is efficient or when additional memory is not a concern, right? On the other hand, choose quick sort when the average case performance is your priority, and since it sorts in place, it requires very little extra memory. It also performs exceptionally well on arrays because better cache utilization, right? And by selecting a good pivot, such as using a randomization or median of 3 technique, you can greatly reduce the chances of encountering the worst case. Okay, and finally, it is noting that many modern programming languages don't rely on just one sorting algorithm. For example, Python uses team sort, a hybrid algorithm that combines the strengths of merge sort and insertion sort, and to achieve real world performance. So there isn't a single best sorting algorithm. The right choice depends on your data, memory constraint and performance requirements, right? So to conclude the lesson, let's review the key takeaways. First, both merge sort and quick sort are based on divide and conquer algorithm paradigm, and these solve large problems by dividing them into small sub problems, solving them recursively, and then combining, right? And then combine, right, to produce the final sorted array. And for merge sort, remember that it is always guarantees a time complexity of O n log n regardless of the input, right? It is a stable algorithm. That means equal elements can keep their original order. However, this comes at the cost of requiring additional memory during the merging process, right? And for quick sort, the average time complexity is O n log n, and making it one of the fastest sorting algorithms in practice. However, its worst case complexity is O n square if poor pivot choices are made, right? Its biggest advantage is that sort in place requires very little extra memory. That's why choosing an effective pivot is crucial for achieving good performance, right? So the key lesson is there is no single sorting algorithm best for every situation. So understand their strengths, limitations and trade-offs allows you to select the most appropriate algorithm based on the problem, right?